All right, to begin the discussion about electron affinity, I want you to recall where we are in our learning objectives. One more down on our list here. This would be item number 10. Figure out which has a larger electron affinity for a pair of elements. How is that done? So let's see. So electron affinity is a new definition. The energy change that occurs when an electron is added to an isolated atom, again in the gaseous state. This is just a definition, but it's worth noting that there is one. The energy change associated with adding an electron to an atom in the gaseous state. Now, the values on this graph show atomic number versus electron affinity. And notice that some of these values are negative. So that means that energy is released for certain elements, and that be favorable. So when they are negative values, the elements are going to easily add an electron, or more favorably add an electron. Other values on the lower part of the chart are actually on the positive side. And these values are going to be the ones that are very unlikely to have an electron added to them for a variety of reasons. So there's going to be group 2A elements, alkaline earths, and group 8 elements. Means the energy is absorbed, and some of them can't be measured, but others are very low because they are not likely. So the favorable ones are all the group 7A elements. They're going to be easily adding electrons. Nonmetals tend to gain electrons, and so their values are going to be large values. And the ones at the bottom are really difficult to do because they're not likely to gain an electron, not whatsoever. So you can't add an electron to noble gases. You can't add one to group 2A elements readily either. So some of these values aren't even shown because you can't measure them accurately. So electron affinity is the definition there again. And so it's the measure of the energy change when electron is picked up, accepted by an atom in a gaseous state, making an anion. How much attraction there is for an atom for its electrons, or an adding electron, is what this essentially measures. And so for something like fluorine being on group 7, we have heard that it makes anions and that electron affinity is very favorable. And so the number there happens to be a negative number, which is described as delta H. We'll talk about delta H in another chapter, but it's an energy change, that's shown in kilojoules per mole there. Pick another value here. The energy change, though, as described as either delta H or EA, means electron affinity. Two ways of writing that. If you looked at oxygen as a gas adding electron, again, it's a nonmetal, and nonmetals are going to tend to make anions. And so how does that one compare to the fluorine? If you add an electron to it to make an oxygen single minus ion, which isn't necessarily its stable form, well, it's going to be a lesser amount of energy, but still favorable. And so its electron affinity corresponds to that smaller value. But again, these are kilojoules per mole. So the more negative the value, the more likely the element is to pick up an electron. So oxygen is less likely to pick up one electron than fluorine. Fluorine really has a strong tendency to pick up electrons. They both do. They're both favorable, but one is more than the other. These are going to be determined experimentally by removing electrons from an anion. Some things are very difficult to measure. They're just plain unstable. And so if we're looking at these examples on the graph, that's why some of them were nearly zero values. Looking at this chart in another variation with more detail, this one is a little deceptive. The electron affinity on the left, the vertical axis, is not shown with negative numbers. Electron affinities are actually negative values, and they're increasingly negative as you go from left to right across a period, that direction across a row. So think about lithium, carbon, fluorine. The value gets much greater each row. Sodium, silicon, chlorine. We're looking for overall patterns here, not looking at the intricacies of the bumps in between. And so that's a general thought. They're going to increase going from left to right across a period. The ones on the left side of the periodic table have very low affinity for electrons. They don't want to add electrons easily. And that would be typical for things that are metals that don't lose. They would prefer instead more favorable to lose electrons. The other pattern to notice is that metals always have lower electron affinities than the nonmetals. The nonmetals are high, the metals are low. And interestingly, there's little variation within a group. So the halogens are all kind of high up here at the top, but they aren't so different from one another. They all have similar electron affinities, especially when you compare them to something from another group. So group 4 elements are like carbon, silicon, germanium, and tin. They're all kind of similar in their ability to pick up an electron. And group 1 elements, this is group 4A, and group 1A elements are the least likely of the ones shown highlighted here. They're not likely at all to pick up electrons, but you could measure it, it's just not very favorable. So very little variation within the group, interestingly, but the metals are always lower than the nonmetals. That concludes my extra information for you about electron affinities.